Hey guys, welcome back. Got some requests to do a video on exponential functions, so let's do it. Also got a request from my nephew to make these videos a little more interesting by adding some background music. So if you'll help me out, turn on some smooth jazz in the background and listen along. All right, so we've all seen videos about exponential functions and whatnot, and there's some great videos out there by some brilliant people. But I'll add my intuition into the mix. I think it'll help. I have a DSP background, digital signal processing, so I'm going to give you kind of the signal processing slash the digital version of this intuition, so it might help a little bit. Before we get into that, let's just kind of describe the basic exponential curve. So you guys have seen this, it's been called many things, hockey stick, that damn hockey stick everybody wants. I keep hearing about, companies want this as their growth graph. A lot of things in nature follow this kind of graph where you have some variable, usually let's say time, but it could be any other variable, and you have some function here. Y is a value, y is a function of t, right? So when we say exponential, really what we're talking about is because the function usually has the shape y equals some number. Okay, let's say it's some any random number. Let's call it k, and then to the power of x, or some fraction of x. It could be k to the power half x or 3x or whatever you want to be. But in the simplest form, it looks like this. And it's called exponential because x is in the exponent. So this is called the exponent. Okay, and this is called the base, or maybe it's called a mantissa, I think. I'm not sure, actually double check my work here. But it's some number that's fixed and it's raised to the xth power, or in this case, it's t. So let's fix that real quick. Oops. Let's put a t in here. So k to the power of t. Okay? So why is this interesting? Well, it's interesting because it has this nice property, or really interesting property, where at any point in the graph, let's say we take this point over here, this corresponds to some value t, and this corresponds to some value y over here. Okay, so let's call it like t naught or y naught, because why not? So it has this nice property where the slope of the graph, i.e. how fast it grows. Okay, if you remember your calculus and Newton's work, this is the slope. It's basically how vertical, how steep the graph is at that point. So exponentials have this really cool property where anywhere you are on the graph, how steep the graph is at that point is proportional to the value y at that point. Okay, so if you think about that, that has the crazy property of, as the graph goes on to the right, i.e. as it grows, it accelerates in its growth. It gets faster and faster. So the more you are in this direction, the faster the growth of the graph is. It's not just that the graph is higher. So I mean, compare that, let's say, to a straight line. So a straight line, it's still the case as you go to the right over here, as the value of t goes up, the value of y will go up, but it doesn't accelerate. The slope of a line is constant. That's kind of the definition of a line. So in this case, the exponential curve, the slope, how steep it is proportional to the value of that function at that point in time. So that's what makes it crazy. Okay, that's what makes it kind of hard to be intuitive, or hard to think about it intuitively. And that got me thinking last night, why aren't humans intuitively adapted to understand the exponential function? It's kind of strange because we see this exponential function everywhere in nature, especially when it comes to growth of bacteria and, say, viruses, right? So you have this situation, for example. You have the situation where there's one person that's infected and they go on to infect two other people. Right, and then let's say they recover, but now you've got two people that are infected with the virus. Then each one of those guys goes on to infect two more people, and so on. And so even if these recover, what you have here is a situation where the amount that it grows at every level, okay, the amount that the amount of people that are infected at each new generation, let's call it, the amount that is added at each level is proportional to the amount at that level. So in this case, for example, if we're looking at this level, there were 4 people infected. We know that the next step, it's going to be proportional to this amount, 4. So it's going to be 2 times 4, right? So you get 8 over here. And then we know in the next step, it's going to be proportional to now this level. So it's going to be 2 times 8. The next step is going to be whatever x is times 2, right? So in this case, this is a simple y equals 2 to the x kind of function. At each level represents let's say, new generation, and it's defined by this function over here. So you see how you have this situation where the more virus you have, the more you'll infect. It's growth in an exponential way, okay? So this is interesting. I mean, so why don't we have intuition for this? So there's kind of some good reasons, but let's talk a little bit about some examples of exponential functions. So growth is a very common one, growth of bacteria. Another one is, you might have not thought about this, but explosions. So think of what an explosion is. You have, let's say you're talking about nuclear fission. You have, some atom, like a uranium atom. It's really the nucleus of a uranium atom. And you can think about, let's say something causes this atom to split, releasing energy. And once you split, this shoots off some particles. And then this particle can go on to split another atom, right? Let's just draw it this way lazily. And so this now can split, which can cause other neutrinos or whatever shoots out with high energies to split more atoms, and so on. So it's a chain reaction. So explosions are really exponential functions. And if you think about it, the process keeps going on, but it doesn't keep going on forever, okay? So why does it stop? So I think this is why, and I'm just speculating here, but I think it's a reasonable guess. The reason why us humans don't have intuition for exponential functions is that exponential functions are usually capped. So it's very rare that in nature you see something like this that keeps going on forever. This is rare. What usually happens is that you see something where it grows for a while exponentially, and then it caps off and turns into a so-called sigmoid or logistical curve. So that is much more likely because there's limited resources. So the fact that you have exponential growth or explosion, you have an exponential explosion against a finite resource of some kind, let's say food or space or fuel, nuclear fuel, it runs out and the growth stops. The exponential curve turns first into kind of a straight line, kind of a linear phase over here. As a matter of fact, this is called the inflection point. When things start to slow down, come back. This is what we're hoping for the COVID situation. We want the inflection point to arrive and to bend the curve so that we slow down the number of infections. Right now, we're in this phase over here. Unfortunately, we're kind of growing pretty explosively, and it's hard to comprehend. Hospitals can't adapt quickly because everybody's kind of used to a linear phase of growth or even a logarithmic phase, something like this, not the exponential phase. Okay, so I think because there's always exponential growth against limited resources or a cap, we're evolved to kind of think in logarithmic or at most linear ways and not really explosive exponential ways. Okay, so that's pretty important. There's an amazing guy, amazing mathematician by the name, I believe, Albert Bartlett. Let's see if I can write that. So yeah, it was Albert Bartlett, and he has some videos online. You can check him out. He once coined the term or phrase, said something along the lines of, I'm paraphrasing it, along the lines of, the worst thing, the greatest shortcoming of the human species is the failure to understand the exponential function. And he has an actual lecture online. I highly recommend you go watch it. Just search on YouTube for this guy. Maybe I'll put a link in after this. It's just a fantastic lecture. And he has this really cool analogy of, imagine you're a bacterium in a jar. So you've got a jar, and every minute the population doubles. You're kind of in an exponential situation. Well, 3 minutes before midnight, he calls it, right? So it's like, let's say you double every minute, and it's like 11:57 or whatever it is. It's 3 minutes before midnight. Well, 3 minutes before midnight, the jar, if you're a bunch of bacteria inside a jar, it'll only be an eighth full, right? It's like an eighth of the jar full. And if you're a little bacterium over here, you look around and you see this massive space ahead of you. You're like, wow, we'll never run out of space. I mean, we've got so much resources over here. Why do we have to ever worry about finding new jars to live on? We can live here forever. Look at all this massive land we can expand into, not a problem. Well, 1 minute later, you're suddenly at a fourth of the jar, and you might have the same thing. You're like, okay, it's a little shit, but maybe we can still survive this and expand into the jar. There's still space. Well, and a minute later, you're halfway there, and even a minute before midnight, you look around and you're still like, well, yeah, it sucks, but look at that, we still got space. Well, at midnight, you're suddenly just right at the top here, you're full to the brim, there's no more space, and bacteriums start to die because of overcrowding. So it's a really cool analogy with how it catches us by surprise. Exponentials always catch us by surprise because of this explosive nature. Okay, so there was an amazing mathematician by the name of, I forget his first name, I think it was Leonard or something. Forgive me for botching it, but his last name is Euler. You've probably heard of this guy, pronounced Euler. Amazing mathematician. He basically wanted to really understand the exponential function, everything about the exponential function and all that. And he did a lot of work to really move humanity forward in terms of mathematics for exponents and exponentials. But one of the things I want to talk about really, which is really cool, is like I was saying earlier in the video, is the quantized version or the digital version of the exponential function. So we can talk about, we showed the graph here, how we can have this is a continuous version of an exponential function. But imagine we had a discrete version or quantized version where you just have discrete data points. Okay? There's nothing in between them, it's just discrete. So let me redraw that. So in signal processing or in digital signal processing, we will show a graph that looks something like this. It's a value here, and then another value here, another value here, another value here. It's like, in a sense, reality doesn't exist between these 2 points. You've just got a first sample. So this is usually called n, and this is, let's say, a function y. And we say this is n of 0. This is n of 1 over here, n of 2, etc. So imagine this property where at each point over here, the amount that you will add, right? So let's say you're looking at this point over here. The amount that you'll add next will be proportional to the difference between two of these consecutive points. So let's write that out a little bit. So let's say we say that the difference between, so let's say, let's call it y of n plus 1, horrible handwriting over here, minus y of n, okay, is equal to the current value of the function, y of n. Okay, that's pretty important. So let me just rewrite this. So we want to say that y of n plus 1 minus y of n is equal to y of n, which means the difference for the next step is equal to the current value that I'm at, right? So because here you get y of n plus 1 is equal to 2 y of n. Well, guess what? Guess what this is in signal processing? This quantity over here is actually the derivative. It's kind of this cool property. In discrete time or in discrete mathematics, the derivative is just a subtraction. It's a difference, which is really cool. This is sometimes called the right-handed difference, which is kind of analogous to the right-handed derivative for you geeks. And interestingly, the integral, okay, like the integral in the continuous case, maps to a simple sum in the discrete case. So everything kind of gets simpler in the discrete case. So you have the situation where in the discrete case, derivatives are simply just subtractions of two data points, right? And so if you have this relationship that says the derivative is equal to the value of the function itself, then you end up with an exponential. And indeed, if you work out the math here, we can go through this, it's relatively easy, and you can just show that this is indeed the function 2 to the n. You have this y of n is really 2 to the n. And indeed, the natural base for discrete exponentials is 2, while in the continuous case, it's actually, so if you have a f of x in the continuous case, the natural base is the value e. It's a little bit confusing where this e comes from, but e is the number 2.71828, blah, 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 blah. I can do another lecture if you want on how this appears in nature. This is a number just like pi. It pops up everywhere, and it's really fascinating the more you dig into it. But suffice it to say, this function has this cool property, which is the derivative of that function is itself. And then this function has the same thing. The difference, if you were to take the discrete derivative of this function, it will be itself, i.e., for the continuous case. So if we have f of x equals e to the x, then df of x by dx, i.e. the derivative of this function, is also e to the x. And then if you take a second derivative, which is the derivative of this function again, d2 f of x by dx squared, it's also e to the x, which if you think about it intuitively, this has this weird behavior, which is like the function and the rate of its change is the same, and the rate of change of its rate of change is also e to the x, and the rate of change of its rate of change of its rate of change is e to the x, etc. So that's why you have, again, this explosive quality to it. Okay, so we can keep going on and on and on, and I wanted to kind of derive where this e number comes from, but maybe we'll do that in another video. This is very fascinating. It comes up, in all sorts of stuff, like I said, in nature. One of the really cool things in signal processing is that you can model, as a matter of fact, this is called Euler's formula. Euler's formula. You can model sinusoids or sine waves using exponentials as well, using this crazy, awesome formula. E to the I theta is equal to cosine theta plus I sine theta. Now I here is a crazy number, which is the square root of -1. And we can get into all that. But basically, since you can decompose any signal into a sum of cosines and sines, and you can write any sum of cosines and sines as exponentials, you can essentially model everything in the universe and how it works using just exponential functions. And that turns out to be a really awesome and powerful property. Anyway, we don't want to go too deep into this, but let me know if you have questions, and I can keep going, but we'll cut it short for now so we don't bore my nephew too much. All right, bye for now.